Good morning friends. Let's start assignment 6, contour integration. First result is integration from minus infinity to infinity x cos of ax over x square minus r square dx equal to 0, where a is strictly negative. And second one is integration from 0 to infinity x sine of ax over x square minus r square dx equal to minus pi by 2 cos of ar. So let's start with the proof. Now because I'm having cos of ax or sine of ax in the numerator, so they will be changed into e the power iota az. But here it is given that a is strictly negative, so I will change them into e the power minus iota az. When this a is positive, change into e the power iota az, and when this a is negative, change this to e the power negative iota az. Rest of the variable x, just replace that with z. So we will integrate fz equal to, yes, in the numerator, write z into e the power negative iota az over, this is z square minus r square. So we will integrate this function along the contour c, where c is a contour indented at, alright, putting denominator equal to 0, we get the points z equal to plus minus r. Okay, so let me write the contour is indented at z equal to minus r and plus r. If you look at this contour, this gamma 1 and gamma 2 are the semicircles having the radius ρ1 and ρ2 respectively. This tau is a semicircle in the upper half plane with radius capital R. Please remember, for semicircles we will tend their radius to 0, and for this bigger semicircle tau, the r is very large. So we take r, the limit of r to be infinity. Alright, what is this point? This is distance minus r, so this point will become, the radius is minus ρ1 on the real axis. The value of the radius is minus ρ1 on the real axis. So this point is minus r plus minus ρ1, which is minus ρ1 minus r. And then this point will be minus r minus of minus ρ1. We have to subtract the radius here. So this will become minus r plus ρ1. And then this is capital O, this is plus r. So this point will become r minus ρ2. Here ρ2 is, its value is positive on the real axis. And this point, we have to just add the radius to r. So this is r plus ρ2. Right? And this is negative r and this is capital R for the bigger semicircle tau. So we will integrate first along the real axis, then along this curve, then again along the real axis, then along the second curve, then along the real axis, then along the semicircle tau. So writing, alright. Now assume r to be positive. Now since fz is analytic inside and on C, and the points are lying outside the contour, right? So by Cauchy's theorem, the complete integration over C, fz dz is equal to 0. All the points lie outside the contour where they are indented. Alright, so let's integrate. This C is splitted up into so many integrations. So first the integration is along real axis. So I write f of x dx, and the limits are from minus r to minus ρ1 minus r. Right? And then the integration is along curve gamma 1. So the function should be in z. Again, the integration is now along the real axis. Write the function in terms of x. And then along gamma 2, it is fz dz. Again on the real axis, write function in terms of x. And for the semicircle tau, write the function in terms of z. So we have to write the function in terms of x whenever the integration is along the real axis, and we write the function in terms of z whenever the integration is along the curves. Right? Simple? Alright. So now we will calculate the integral, this one, and this is obviously 0 by Jordan's lemma, right? So, and rest of the integration, they will be merged together. Alright, for gamma 1, limit rho 1 tends to 0, integration over gamma 1 fz dz, what is the formula? It is iota theta 2 minus theta 1. Theta 2 is 0 minus pi. Then limit z tends to, where it is indented, at minus r, first one. Then z minus r, which is z plus r, and then f of z. So this is equal to minus pi iota limit z tends to minus r, z plus r, writing the value for this function, that is z e the power minus iota az over, it is z square minus a square, I guess. What is the function? It is, yes, z square minus r square. Right? So this is equal to, now minus pi iota. Can I write z square minus r square as z plus r and z minus r? So z plus r will be cancelled with z plus r. So this will become limit z tends to minus r. This will be cancelled out. Z e the power minus iota az, and z minus r remains in the denominator. So putting the value of z as minus r in here, we get, this is equal to minus pi iota by 2 e the power iota ar. Right? Now the second integral over gamma 2 fz dz, that is iota 0 minus pi, limit z tends to the second point where the curve is indented, that is positive r, and then z minus r, f of z. So this is minus pi iota, limit z tends to r, this is z minus r e the power minus iota az. I'm just making their factors. So z square minus r square is written as z minus r and z plus r. So this is cancelled out. So just putting the value of z here as r, that will give you minus pi e the power negative iota ar over 2. Let me write this. Over here, one and the same thing. Alright, since z over z square minus r square tends to 0 uniformly as z tends to infinity, and this is meromorphic in the upper half plane as it has no singularity there. Yes? Alright, so by Jordan's lemma we write limit r tends to infinity, the integral over tau, and this is e the power minus iota az, z over z square minus r square dz is equal to 0, which implies, because it is a function of z, I'm writing f of z dz equal to 0. Please remember, here a is given to be negative, right? So minus a will become positive. So now letting rho 1 tends to 0, rho 2 tends to 0, r tends to infinity in our main equation 1. Here. So this r minus r will become minus infinity, and this will become upper limit will be minus r because rho 1 is tending to 0, and we will write the value of this integral here, and then this limit will become minus r2 plus r because rho 2 is also tending to 0, rho 1 is also tending to 0, and for gamma 2 I will write the value here which just we have calculated, and then this integration will from 0 to infinity, sorry, from r to infinity, and then this is obviously 0 then. So writing the values and putting all the values in this integral, I get, this implies this is minus infinity to minus r f of x dx minus the value is pi iota over 2 e the power iota ar plus this is from minus r to plus r f of x dx, and then writing the value for the fourth integral pi iota over 2 e the power minus iota ar plus this is from r to infinity f of x dx plus the integral over tau, very smart, 0. So this is equal to 0. Now merging these integrals and taking these two on the other side, we get integration from minus infinity to infinity f of x dx equal to, alright, taking all these two to the other side, this will come pi iota over 2 e the power iota ar plus e the power minus iota ar. Do you remember the formula for the cos of ar, which is e the power iota ar plus e the power minus iota ar over 2. This is the formula. So I'm writing the value of this numerator here. So this is equal to pi iota over 2 cos of ar. And writing the value of this fx over here, which is x e the power minus a iota z, sorry, x over x square minus r square dx. Right? Now equating the real and imaginary parts. If I equate the real part, I will get cos in the numerator. If I equate the imaginary part, I will get sine in the numerator. So let's equate the real and imaginary part. So let me equate first. Equating the real part first, we get the right hand side is imaginary, right? So there is no real part in the right hand side, so that will be 0. And in the left hand side we have x into cos of minus ax, right? So this is minus infinity to infinity x cos of minus ax over x square minus r square dx equal to 0. And we know that cos of minus ax is cos of ax, very good. So this is x square minus r square dx is equal to 0. This only we have to prove, right? So first result is done. And now equating the imaginary part. Equating the imaginary part, we get, alright, So integration from minus infinity to infinity, x into, yes, sine of minus ax, very good. So it is divided by x square minus r square dx, and this is equal to, because I'm having iota over here, so this is pi by 2 cos of ar. Sorry, this is twice cos of ar, right? So 2 and 2 will be cancelled out. I'm very sorry. So this is pi iota cos of ar. Sorry, alright. Thank you. Okay, so the imaginary part will become pi cos of ar. So this is pi cos of ar with, is there any negative sign? No. Alright, what is sine of minus ax? It is minus sine of ax. So minus infinity to infinity x sine of ax over x square minus r square is equal to pi cos of ar. Now because this is your even function, so I can write this integral as twice 0 to infinity. So this will become negative twice 0 to infinity x sine of ax over x square minus r square dx equal to pi cos of ar. And then this implies taking this minus 2 to the other side, I get 0 to infinity x sine of ax x square minus r square dx equal to minus pi by 2 cos of ar. So the second result is now proved, right? So by equating the real and imaginary parts, we have proved both the results. So thank you so much for watching this video. God bless you all. Have a very nice day. Goodbye.